So the central nervous system is protected in several ways. This material is covered on page 139 to 140 of your text. First, we have bony structures, the cranium and the vertebral column, that protect the brain and spinal cord respectively. We also have the meninges, the dura, arachnoid, and pia mater, which you can see from outermost to innermost here, and also along the spinal cord, providing some additional level of protection. We also have the cerebrospinal fluid, which can help to protect the brain in a couple of ways. And importantly, we have the blood-brain barrier. And we have pictures of several of these on subsequent slides. The cerebrospinal fluid is made and produced by modified ependymal cells in the choroid plexuses of each ventricle. And so it's produced in the choroid plexus, it'll circulate through the ventricles, and ultimately will exit through the fourth ventricle at the base of the brain, and it will flow through the subarachnoid space between the meningeal layers and eventually be reabsorbed from the subarachnoid space into the venous blood. So that is how the cerebrospinal fluid circulates. People who have too much cerebrospinal fluid develop hydrocephaly, which can become painful, causing terrible headaches, and so needing greater clearance. In a typical capillary, most places in the body, you'd find some small pores between epithelial cells allowing some substances to pass. Other substances also could pass directly through the cells, but astrocytes have processes that help to surround these capillaries, which are going to be a barrier. In addition, you would find that rather than having these pores, the epithelial cells have tight junctions, which means that any substance to get into the brain is going to have to go through these cells, and then ultimately will need to pass between these astrocyte processes, meaning that there's going to be some regulation of movement. So for example, if your blood and body fluids were to become too acidic, that would be bad for the brain. Hydrogen ions actually can't pass through the blood-brain barrier. They remain in here, although as we'll see later this semester, they might increase carbon dioxide here, and CO2 can be transported out, and increasing CO2 here might increase hydrogen ions. This also has important implications for drug delivery, in that it's typically somewhat hard to deliver drugs to structures in the brain because it has to be a substance that's able to pass. So for example, people with Parkinson's disease don't produce enough dopamine in parts of the basal ganglia. As a result, they need to be given dopamine exogenously, but dopamine would not pass the blood-brain barrier. So they're given L-DOPA or levodopa, which can be brought into the brain, and then it is used to make dopamine once in the brain. So one example of why we should study nature is understanding drug delivery. Lamprey are one of our deep evolutionary ancestors, and they, as it turns out, their immune system has a factor which can pass the blood-brain barrier and has been used now to deliver chemotherapeutic agents to individuals with gliomas. So these lamprey, which are normally parasitic fish, have this immune effector molecule which can be tied with a chemotherapeutic agent and thus delivered to the brain, providing us with a new opportunity for delivering drugs to the brain.